Hi, I'm Danny Sawyer, lead author of Exploring Exploration with Foundation Agents in Interactive Environments, and I'm excited to present our findings to you today. So the motivation for this work is that Foundation agents are typically evaluated in single-turn math and reasoning problems, where all the information is provided up front and doesn't have to be actively discovered by the model. And this theme of providing information versus active discovery is also true in agentic benchmarks, where even if benchmarks are multi-turn, they don't involve exploration. And exploration is an important skill for these models if we want to replicate human capabilities from even just learning a video game for the first time to actually doing science. So we want to answer the question, how well can frontier Foundation agents autonomously explore interactive environments to test hypotheses? In contrast to previous benchmarks, where they evaluate exploration, such as Discovery World or Science Agent Bench, where they look at end-to-end exploration on a diversity of tasks, we use some more abstract settings to really break down exploration into three measurable capabilities and in comparison to known optimal and random baselines. Three capabilities we look at are efficient information gathering, meta-learning, and strategy adaptation. We use two environments to test these capabilities. The first is Feature World. This is a stateless setting akin to a bandit problem. It involves both text-based and 3D versions, and it tests information gathering efficiency, which can be thought of as how well can the model ask the right questions? How well can it take actions that maximize information gain? The second is Alchemy, which is actually a previously published benchmark for RL agents. And this is a more complex multi-trial environment that has latent causal rules. We use a text-based version, and we use it to test meta-learning, or learning to learn, and strategy adaptation, which is how well a model can learn a new strategy when the previous one is no longer applicable. So first is Feature World. I'll illustrate it with the text version. Basically, you just have different objects, each of which has a color and a shape property. The model receives a reward of 1 or 0 when it selects an object. So typical exploration trajectory, optimal exploration trajectory would look like this. Is the color blue, you select a blue pyramid. This was not correct. So to maximize information gain of the next action, you choose an object that is both not blue and not a pyramid. The red sphere was also incorrect. And so the correct property must either be cube or green. So you select green pyramid because that is correct, and you have selected a pyramid before that was incorrect, you know that the correct property is green. In a 3D version of this, the model is in an embodied environment and actually has to use its vision capabilities to distinguish which objects were picked up and which ones to pick up next. So for instance, it picks up red pyramid, that was incorrect. Red cube, incorrect. Tries a blue plank, that was correct. So it thinks maybe plank is correct. Tries a purple plank, that was incorrect. So now it knows that blue is the correct property. And so it's going to put the blue objects in. And of course, that is correct. And blue pyramid, correct again. So we looked at a variety of models, ChatGPT, Claude, and various versions of Gemini on these tasks. For the single feature tasks described above, both in the case with just only 3 properties, and then as we increase the number of colors and thus the number of objects to increase complexity, models pretty much all performed optimally. And so we then tried to increase the complexity of the reward function. And we did this by adding a third property, texture, and then the rewarding feature is a conjunction of two properties. For instance, a shiny and blue could be the correct conjunction. And in these cases, especially as we increase complexity, a lot of models did struggle more. However, if you look at the ratio of successful episodes, ratios are still pretty high, like above 80%, even as you increase complexity for most models. And interestingly, Gemini 2.5 Pro actually is optimal across complexity levels. And this shows that the frontier of foundation agents is actually pretty much optimal at efficient information gathering. So this stands in contrast to conclusions from these previous benchmarks. And it also shows the advantage of testing multiple frontier models. Since if we only looked at ChatGPT, which I think Discovery World, for instance, only looked at the GPT-4, the conclusion would be that these models are suboptimal. But actually, when we look at Gemini 2.5 Pro and to a lesser extent Flash, we see that these models are optimal, can be optimal at efficient information gathering. So there is this aspect of exploration, albeit a simple one, where these models are optimal. And in the 3D case, the results were a bit more nuanced. We found that out of the box, this is just Gemini 1.5. Results weren't significant when we looked just at overall performance, but if you remove vision errors, then the model is close to optimal. So what this shows us is that the reasoning isn't so bad. It's just like the visual nature of the task adds more errors that impact performance. So to push these models further, we tested them in Alchemy. The way this works is that you have different stones and potions, and the different colors of potions change the stone's properties in different ways. So here, for instance, green changes color, then turquoise changes shape, and yellow changes size. And what you're essentially doing is navigating a latent graph and in order to maximize the value of the stone. So that is what reinforcement learning agents were tasked to do, and what we are now asking foundation agents to do. The way this environment is set up is that you have different trials, each with like a given random set of stones and potions, and the chemistry after 10 trials then changes. So after 10 trials, you complete an episode, and the goal is to maximize score in the episode. So ideally, you want to explore what the graph looks like early on, and then exploit information in later trials to maximize your score. And so what the model looks like is this is pretty much verbatim what the data that the model receives. Just a list of stones and potions. And here's like a little simplified illustration of what the interaction looks like in simplified form. So the model does some exploration, tries different potions. It then makes a summary of these rules, and then in the next trial, from its learned information, it's able to do reasoning and get to the reward faster. So we weren't just interested in the overall score of the model. What we're really interested in is whether the model is able to improve over time. So meta-learning here is defined as when trained on tasks in a given family, does it perform better on other tasks, untrained tasks in the same family? And so to measure this, we look at score improvement as the mean of the last 5 trials minus the first trial, and that's your score improvement. And when we looked at these models, out of the box, we found that actually none of them had significant score improvement over time. And we hypothesized that the models were, because they were able to, as shown previously, take actions in the moment, we hypothesized that they weren't actively distilling principles from their long action histories. So what we did was the kind of a very simple intervention. We just, after each trial, prompt the model to write a summary of its findings. We just say, what did you learn about how the different potions affect the stones? And we did that after each trial. So previously, the model was receiving the full episode history in its context. And now, rather than the full episode history, we first ask the model to write a summary and then feed that back. So this summary is both more context efficient because it's only has to look at the summary and the effects of the current trial. And what we found is that with the summary, most models now do show improvement over time. So they're actively able to, there's this emergent meta-learning capability where the model by default is not kind of in this mode of being able to use its previous information to explore better, but when provided with a summary, it does. To push this farther, we also looked at strategy adaptation. This is inspired by the Wisconsin card sorting task, which measures the function of the dorsolateral prefrontal cortex in humans. It's one of the most recently evolved brain structures and is involved in detecting when a previously effective pattern of behavior is no longer effective and needs to be changed. So in this case, we, rather than resetting the model after the first episode, we silently allow the rules to change. So the graph changes and the model doesn't receive any information about it. All it sees is that its actions no longer have the effect that they used to. And out of the box, the models actually are not able to recover their previous performance. It drops to be pretty much aligned with the memoryless heuristic that isn't able, a heuristic that doesn't take into account previous information. However, when we add the summary, the models are able to recover performance. And so this shows that we really are tapping into, just with these summaries, tapping into this latent capability of the models to actively explore. And so this, in contrast to previous benchmarks, shows that these models do have the ability to integrate information over trials, and that, however, that these skills are currently a bit brittle in the sense that you need like just the right prompt to elicit them. So in conclusion, we're finding that reflection on previous data in context is key. And to be clear, all these experiments were performed in context, so no fine-tuning or other post-training on these specific tasks. We really want to evaluate the capability akin to just dropping someone into, say, a new video game or presented with a new scientific challenge and getting to work with a lot of uncertainty and building knowledge from the ground up. So our key insight is that the major frontier in this exploration isn't just gathering information and selecting optimal actions at the moment, which models are pretty good at, but rather continuously integrating that information. So the ability to improve through adaptive strategies over time is challenging for these models, but it is not fundamentally out of reach. And we showed that we can improve in these capabilities without any kind of complex memory modules. It's really just cognitive structuring through these through a bit of prompting. And so maybe the reason we hypothesize that models are not good at these tasks yet is because in their post-training and pre-training, they're not exposed. They don't have to really reflect on information that they've gathered to then condition how they the next type of information that they receive. So embodied, interactive, and multi-trial environments are going to be crucial for measuring progress and guiding future development in these skills. Thank you.